In this module, I'll run through a meta-analysis that looks at the risk of death for patients in their 80s following mitral valve repair or replacement. The effect size index is the risk of an event. I recommend this video if you're planning to work with the risk of an event in one group, such as incidence or prevalence. I'll cover the following items: how to enter data, how to run the analysis, how to estimate the mean effect size, how to understand heterogeneity in effects, how to report the results, and how to create plots. I'll be using the software Comprehensive Meta-Analysis, or CMA. Our website is metaanalysis.com. There, you can download a free trial of the software and also the datasets used in this video. Overview. This analysis includes 25 studies of patients aged 80 years or more undergoing surgery for mitral valve repair or replacement. The outcome was the proportion of patients who died during or immediately following surgery. The results of this analysis will be generalized to comparable studies, and so the random effects model was employed for the analysis. The analysis was performed using a logit transformation of the data. This is a reanalysis of a systematic review published by Bianchari et al. In 2013. If you're interested in the specifics of this analysis, please don't rely on this video, but consult the original paper. Let's start by looking at the data in Excel. The file is called mortality.xls. Here's a column here with the study names. This column has the number of patients who died, and this column has the sample size. We're going to be using the risk as the effect size index. I want to copy this data into CMA. I'll highlight all the relevant cells. Notice that I'm including the row with the labels. I click Ctrl-C to copy. I'll open CMA. I'll close this box. I click in this cell, and I click Ctrl-V to paste. Next, I want to take these labels and move them into the header. I click Format, Use First Row as Labels. At this point, the labels are correct, but I still need to identify the function of each column. On the menu, there's a button that I can use to insert columns, and there's a separate button that I can use to identify the function of columns. Since the columns are already in the grid, and I want to identify their functions, I'll use Identify rather than Insert. I click on the first column, and then I click Identify Column for Study Names. And the program changes the header to Study Name. I click Identify Column for Effect Size Data. The program opens this wizard. CMA will accept data in many formats, and so I need to tell the program what format I want to use. I also have the option of entering data for some studies in one format, and for other studies in a second format, and so on. At the bottom, I choose Show All 100 Formats, and I click Next. Here, I choose the second option button. This is the one that will allow me to report the risk in one group rather than comparing the risk in two groups. I click Next. On this frame, I choose dichotomous data because I'll be looking at the number of events. Then I choose raw data, and now I choose events and sample size. If I were inserting these columns, the Finish button would light up. However, since the columns already exist and I need to match each column with its function, the Next button lights up. I click Next. Events are in the column called Dead, and sample size is in the column called N. I click Finish. By default, the program is displaying the event rate for each study. And it's also showing the logit event rate for each study. I right-click on the yellow columns. I select Customize the display. At the bottom, I add a check mark for Show the standard error and Show the variance. And I click OK. At this point, it's a good idea to save the file. I click the Save icon, and I give the file a name. Now I'm ready to run the analysis. I click Run Analysis. At the bottom of this screen, I can choose either the fixed effect model or the random effects model. I choose the random effects model for 3 reasons. First, it allows me to take account of the study-to-study variance when assigning weights to each study. Second, it allows me to assess the dispersion in effect size across studies. And third, this model will allow me to generalize from the studies in the analysis to the universe of comparable studies, which is what I intend to do. Next, I'd like to set the scale for the forest plot. I right-click on the plot, I select Scale, Customize, and I set the scale to 0 to 1. I'd like to sort the studies by effect size so that I can get a general sense of how widely the effect size varies across studies. I right-click on the column labeled Event Rate. I click Sort from Low to High. I get the sense that the event rate in most studies falls in the range of around 2% to 37%. There is one study with an event rate of around 50%. However, that study has a large confidence interval, and it's not clear how much weight that study will be assigned in the analysis. In any event, this is only intended to give me a general sense of the dispersion. We will compute the actual dispersion momentarily. And finally, I'd like to display the actual numbers for each study. I click this button, and the program inserts a column with the number of events and sample size. The pooled estimate of the event rate is 0.166. We see that here and here. On average, in the universe of populations that are comparable to those in the analysis, roughly 17% of patients will die as a result of the surgery. The confidence interval tells me how precisely we've estimated the mean. The confidence interval is roughly 0.14 to 0.19. We see that here, and we see it here. This tells me that the mean effect size in the universe of comparable populations probably falls in the range of 0.14 to 0.19. These columns test the null hypothesis that the true event rate is 50%. We have no interest in that null hypothesis, and so I will hide these columns. I right-click on any of these columns. And I remove the check mark for the z-value and the p-value. Next, we want to look at how much the effect size varies across studies. This is called heterogeneity. To avoid confusion, let me address a common mistake. A moment ago, I spoke about this line, which reflects the confidence interval. Many researchers believe that this line tells us something about the dispersion in effects. It does not. It tells us how precisely we have estimated the mean effect size. It says nothing about how widely the effect size varies from study to study. This line is sometimes displayed as it is here, and is sometimes displayed as a diamond, as it is in this version of the plot. But in either case, the meaning is the same. The confidence interval is an index of precision, not an index of dispersion. It tells us nothing about how widely the effect size varies across studies. To get a general sense of the heterogeneity, I can sort the studies by effect size as I did a moment ago. However, this plot is not as informative as we might expect for several reasons. One reason is that some of the dispersion that we see here is due simply to sampling error. The dispersion of true effects, which is what we care about, could be substantially smaller than we would expect based on this plot. A second reason is that we're looking at the distribution of risks in 25 studies, but we're trying to estimate what the distribution would look like in a much larger universe of studies. In that universe, we would expect to see populations that have lower or higher risks than the ones we see here. So, to compute the amount of dispersion, we would do something similar to what we do in a primary study. We compute the standard deviation of effects, and then we compute an interval based on the mean plus or minus 2 standard deviations. If we can assume that the risks are normally distributed in the relevant units, we expect that the true effect size in 95% of all comparable populations will fall within that interval. I'm going to switch to a plot that actually shows the entire distribution of effects. Unlike the current plot, which shows the effects in R25 populations, this plot shows the distribution of effects in the universe of all comparable populations. I've set the scale to go from 0 to 1. The mean is 0.17. I'll plot that here. I can add the confidence interval and the caption. The caption reads, the mean effect size is 0.17 with a 95% confidence interval of 0.14 to 0.19. In other words, we've estimated the mean as 0.17, but the true mean could fall anywhere from here to here. As I mentioned before, all of this deals with the average effect size. It says nothing about how the effect size in individual studies varies from the mean. Now let's look at the dispersion in effects. I'm going to present 3 possible distributions. We want to know which one applies in our analysis. Here is one possible distribution. This line shows the distribution of effects. At one extreme, there are some populations where the risk of death is 10%. At the other extreme, there are some populations where the risk of death is 27%. The actual numbers are presented in this caption, which reads, the true effect size in 95% of all comparable populations falls in the interval 0.10 to 0.27. This interval, 0.10 to 0.27, is called the prediction interval. If I was asked to predict the risk of death for patients in any one population, selected at random from the universe of populations comparable to those in the analysis, I would predict that the risk would fall in this interval, and I'd be correct some 95% of the time. In the other 5% of cases, the true effect size would fall to the left of here or to the right of here. So the prediction interval simply gives us the endpoints of the plot. The distribution is assumed to be symmetric in logit units. It appears to be asymmetric because this plot is in risk units. So that's one possible distribution. Or does the distribution of effects look like this? At one extreme, there are some populations where the risk of death is 6%, and at the other extreme, there are some populations where the risk of death is 39%. In this case, the prediction interval is 0.06 to 0.39. Or does the distribution of effects look like this? At one extreme, there are some populations where the risk of death is 1%, and at the other extreme, there are some populations where the risk of death is 84%. These are three possible examples of what the distribution of effects might look like. Of course, there are an infinite number of other possible distributions. I've picked these three to illustrate my point, which is simply that when we ask about heterogeneity, this is what we have in mind. We want to know what the distribution of effects looks like. Why is it important to know which of these applies? Well, if the distribution looks like this, we would conclude that the risk varies substantially across populations. This tells me that it would be important to understand what factors are associated with these studies over here and with these studies over here. For example, suppose it turns out that these studies were based on patients where the surgery was elective, while these were based on emergency cases. In that case, it might be possible to provide more useful information about the risk to future patients. For patients similar to these, we could predict that the risk would be in this range, and for patients similar to these, we could predict that the risk would be in this range. Still, there would be a limit to how much we can improve our prediction. The risk will never fall below 10%. By contrast, suppose the distribution of effects looks like this. It might be possible to identify populations where we can tell people that the risk of death is 6% and others where the risk approaches 40%. This would provide people and their clinicians with better information for deciding whether to undergo the procedure. Similarly, suppose the distribution of effects looks like this. It might be possible to identify populations where the risk of death is 1% and others where the risk exceeds 80%. Clearly, this kind of information would be extremely important in the decision-making process. At this point, we're not yet trying to identify factors that might be associated with lower risk or higher risk. We will deal with that in later modules. Rather, for now, we simply want to know what the distribution of effects looks like. So, which of these three plots corresponds to the actual distribution of effects in this analysis? I would assume that this information is included in any paper that reports a meta-analysis. As it turns out, however, I would be wrong. There are three statistics that researchers typically report to describe heterogeneity. To see these statistics in CMA, I click Next Table, I scroll over to the right, and the statistics are presented here. These are the Q value, along with its degrees of freedom and p-value, the I-squared statistic, and tau squared. However, as we will see momentarily, these statistics don't actually tell us how much the effect size varies. The first statistic reported is the Q value, along with its degrees of freedom and p-value. In this case, the Q value is 65.668, the degrees of freedom is 24, and the p-value is less than 0.001. On that basis, does the distribution of effects look like this, or like this? The answer is there is no way to know. It could be any of these. The next statistic reported is I-squared, and in this case, I-squared is 63%. On that basis, does the distribution of effects look like this, like this or like this? Again, the answer is there is no way to know. It could be any of these. I recognize that this statement will probably come as a surprise, but ask yourself this. I've given you the value of I-square, which is 63%. Which of these plots actually corresponds to the distribution of true effects? You may or may not guess correctly, but your choice will be a guess because I-squared does not provide this information. And finally, the last statistic typically reported is tau squared, the variance of true effects. In this case, tau squared is 0.080 in logit units. On that basis, does the distribution of effects look like this, or like this? It actually is possible to determine which of these is correct based on tau squared, but few people know how. So what statistic does tell us how much the effect size varies? Well, that statistic is the prediction interval. Here, I would report that the true effect size in 95% of all comparable populations falls in the interval 0.10 to 0.27, and that corresponds to this distribution. Where do I locate the prediction interval? If I'm using CMA version 4, I can simply click this button and the program creates this plot. If this looks different from the plot that I showed before, that's because that one used a scale of 0 to 1, and this one uses a scale of 0 to 0.50. This caption reflects the information in that distribution. It reads, the true effect size in 95% of all comparable populations falls in the interval 0.10 to 0.27. If you're using an earlier version of CMA, or if you're using another program entirely, you can still create this plot. To do so, you can download a free program on our website. You would simply enter 4 values as shown here. The mean effect size, the upper limit of the confidence interval, tau squared, and the number of studies. And then click Next to create the plot. To this point, I've explained that the key statistic that addresses the dispersion and effects is the prediction interval. What about the other statistics? What did the p-value, I-squared, and tau squared tell us? Later in this video, when I explain how to report the results of a meta-analysis, I provide a 1-sentence description of each. However, to actually explain what each of these tells us is really a separate lecture. For those of you who are interested, the lecture is available for free at metaanalysisworkshops.com. And this is also addressed in the text Common Mistakes in Meta-Analysis and How to Avoid Them. The relevant chapter is available for free as a PDF on the book's website. I encourage you to take advantage of these resources. A primary benefit of a meta-analysis is that it enables us to see how the effect size varies across studies. We should always be sure to report this information and to do so in a way that is clear and informative. That is, by reporting the prediction interval. There is one very important caveat to all of this. In order to estimate heterogeneity reliably, we need a minimum number of studies in the analysis. The number of studies needed will vary based on several factors. However, we might use 10 as a useful minimum. When there is variation in effects, and there are less than 10 studies in the analysis, we cannot have confidence that any of the statistics related to heterogeneity will be reliable. This includes I-squared, tau squared, and the prediction interval. Next, let's have a look at how we might explain the results. In version 4 of CMA, I can click this button and the program displays this page, which reads as follows. Overview. The analysis is based on 25 studies. The effect size index is the event rate. The results of this analysis will be generalized to comparable studies, and therefore the random effects model was employed for the analysis. What is the mean effect size? The mean effect size is 0.166 with a 95% confidence interval of 0.142 to 0.193. The mean effect size in the universe of comparable studies could fall anywhere in this interval. How much does the effect size vary across studies? The Q statistic provides a test of the null hypothesis that all studies in the analysis share a common effect size. If all studies shared the same true effect size, the expected value of Q would be equal to the degrees of freedom, which is the number of studies minus 1. The Q value is 65.668 with 24 degrees of freedom and a p-value of less than 0.001. Using a criterion alpha of 0.10, we can reject the null hypothesis that the true effect size is the same in all these studies. The I-squared statistic is 63%, which tells us that some 63% of the variance in observed effects reflects variance in true effects rather than sampling error. Tau squared, the variance of true effect sizes, is 0.080 in logit units, and tau, the standard deviation of true effect sizes, is 0.282 in logit units. If we assume that the true effects are normally distributed in logit units, we can estimate that the prediction interval is 0.097 to 0.269. The true effect size in 95% of all comparable populations falls in this interval. And we can export this report to Word. Please note that my intention here is not to have the program write the report. I'm simply trying to ensure that the statistics are interpreted correctly. Next, we might want to create a high-resolution version of the forest plot. I click High Resolution Plot. I click Reset All. I want to set the dimensions of the plot to match the newer version of PowerPoint. If I'm using version 4, that will be the default. If I'm using version 3, I would click File, Page Size and Margins. Then I'd set the width to 1600 and the height to 900. I leave the left and right margins at 50, and I change the top and bottom margins to 35. I right-click on the title. I edit the title to read Mortality in Patients 80+ years of age. Next, I right-click on the plot and click Spacing and Forest Plot Width. There's an area over here called the right buffer. This leaves space on the right side of the forest plot in case I want to add additional columns there. In this case, I don't, and so I want to remove the buffer. I click Right Buffer and Remove. I'd like to add space between the columns. I click Column Spacing, and then I click the button with 2 blue arrows. I want to increase the size of the plot. I click Forest Plot Width, and I click the button with 2 blue arrows. The 2 sides of the plot are labeled Favors A and Favors B. These labels don't apply over here, so I right-click on Favors A, and I remove the text from both labels. Now I'd like to send the plot to PowerPoint. I click File, Export to PowerPoint. The program opens PowerPoint and inserts the plot. Back in CMA, I can also choose colors for slides and modify any or all of the colors. For example, I could set the colors to look like this, and then send it to PowerPoint again. I can also send the plot directly to Word, or I can save this as a file and then import it into any program. Next, let's generate a high-resolution version of the distribution of true effects. I simply click this button to get the plot. I can edit almost any element on the plot. Once again, I'll change the title to Mortality in Patients 80 plus years of age. Again, I can click File, Export to PowerPoint. When we analyze a primary study, we typically perform a sensitivity analysis. This means that we perform a series of analyses to ensure that the results are robust. For example, we might want to ensure that the results were not overly influenced by one outlier. We can do the same thing in a meta-analysis. One issue that we might want to explore is how much impact each study has on the analysis. Recall that the summary effect size is actually a weighted mean of the individual effect sizes. So we might want to see how much weight was assigned to each study. If I click this button, I can display a column that shows the relative weight assigned to each study. Initially, these bars are on a scale of 0 to 100. But to see the weights more clearly, I right-click here. I choose Scale Relative to Maximum. This changes the scale so that the differences among weights are easier to see. Additionally, I can sort by relative weight. I right-click on the weights, and I select Sort from High to Low. It looks like no study gets more than 11% of the weight. That's reassuring. If there was one study that dominated the analysis, we would want to call attention to that in the discussion, and we would also want to identify the impact of that study on the basic conclusions. For example, we would want to know how much the effect size would shift if that study were removed. In this case, there is no study that dominates the analysis, and we can say that in the report. Another thing we might want to do as part of a sensitivity analysis is to assure ourselves that no single study is responsible for the essential conclusions of the analysis. For example, suppose that there was one study which happened to have an extremely low effect size. If this study were removed from the analysis, the mean effect size might shift substantially, and the heterogeneity in effects might become substantially smaller. This would not mean that we want to remove this study from the analysis, but we would want to be aware of its impact on the analysis and discuss that as part of the report. In this analysis, it's not likely that any study will pose this kind of a problem since no study receives more than about 11% of the weight, and there are no real outliers. Nevertheless, we'll run through this as an exercise. At the bottom of the screen, I have a tab for basic stats and a tab for one study removed. I'll click on the tab for one study removed. Now, the row labeled D. Giugiaro does not show the results for D. Giugiaro. Rather, the row for D. Giugiaro shows the results for an analysis based on all studies except for D. Giugiaro. On the row labeled D. Giugiaro, the effect size is 0.169 with a confidence interval of 0.145 to 0.195. This is what we would see on the yellow line if we were to run an analysis using the other 24 studies. As I scan the set of analyses, I see that regardless of which study I remove, the basic conclusions remain unchanged. In other words, the mean effect size never moves to the left nor to the right by enough to change the clinical implications of the finding. So, this plot allows me to report that the results are robust in the sense that the conclusions remain essentially the same with any one study removed. I'll click Basic Stats to return to the standard analysis screen. I will not perform a test for publication bias. The various methods that look for publication bias are based on the idea that a study is less likely to be published if that study's results are not statistically significant. In this analysis, we're looking at the risk in one group, and we're not testing for statistical significance. Therefore, the idea of using these methods to look for publication bias does not apply. Put simply, we cannot suggest that the likelihood of a study's being published is affected by statistical significance if the studies do not test for statistical significance. That's it for this example. For a complete discussion of meta-analysis, consider subscribing to our workshops. These are now available online as well as in person. For information, visit metaanalysisworkshops.com. This is also where you can download the free program to compute prediction intervals. In this analysis, I used the software Comprehensive Meta-Analysis. For information about the software, please visit metaanalysis.com. My name is Michael Borenstein. My email is michael@metaanalysis.com. Please feel free to contact me with any comments or questions.